Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is wind and water power. Our objective is to examine those properties that influence the mechanical power present in a column of moving fluid like wind and water. In the course of this short lecture, I additionally plan to authoritatively answer two of the three most common questions I'm asked about wind turbines. Notably, why they so big, why they so tall, and why they painted white. Let us begin. This lecture presumes the viewer has watched the Introduction to Renewable Energy lecture, available at the Big Bad Tech channel. If you haven't done so already, please do so now and return when you are so qualified. Traditional electrical power production uses an outside mechanical power source known as a prime mover. A turbine serves as the principal means of initially capturing this incoming mechanical power from the prime mover and turning it into rotating mechanical power input to a generator that exports usable electrical power. Coal-fired power plants and nuclear power plants use heat to boil water to produce expanding steam that acts as a prime mover. Renewable resources like moving wind and falling water can additionally act as a prime mover. Steam, wind, and water are fluids composed of particles of moving matter, like bullets, that strike the blades of a turbine and impart a portion of their kinetic energy to the turbine. The kinetic energy present in these tiny individual bullets is dependent upon their mass and velocity. The more massive and quicker and more numerous they are, the more power a column of wind or water contains. The formula used to measure the quantity of mechanical power input in units of joules per second or watts in a column of moving fluid demonstrates its proportion to half the density times the cross-sectional area intercepted by the turbine times the velocity of the fluid raised to the third power. This formula demonstrates that denser fluids, like water, have more power than less dense fluids like wind. This formula additionally demonstrates physically larger turbines intercept more moving fluid particles and can extract more mechanical power than physically smaller turbines. Finally, this formula demonstrates that the speed of the fluid moving through the turbine is perhaps the most influential property in calculating mechanical power input since it's raised to the third power. This means any small increase in speed significantly increases the amount of power present in the column of fluid. Let's try a couple of illustrated examples of this formula to illustrate how different operating conditions influence power input. Along the way, we'll discuss wind turbine power curves, efficiency, and pitch control. Consider a rated 1.5 megawatt wind turbine with a 77-meter diameter rotor operated at three different speeds: a gentle breeze of 3.5 meters per second, a strong breeze of 12 meters per second, and storm conditions at 25 meters per second. Let's say the air density for each of these three scenarios is a constant 1.204 kilograms per meter cubed. Let's use the power formula to determine the power present in the column of wind when used as a prime mover. First, since this is essential to all three scenarios, let's calculate the rotor swept area for a turbine with a 77-meter diameter. Circular surface area is pi over 4 times the diameter squared. Substituting 77 meters into this equation demonstrates the rotor swept area is roughly 4,656.6 meters squared. Substituting the density, area, and speed into the power formula demonstrates that at a gentle 3.5 meters per second, the column of wind possesses approximately 120.2 kilowatts of power. At an increased speed of 12 meters per second, the power formula demonstrates the column wind possesses approximately 4.8 megawatts of power. Finally, in storm conditions at an increased speed of 25 meters per second, the power input formula demonstrates the column wind possesses approximately 43.8 megawatts of power. You will note as wind speed progressively increases from a gentle breeze to a strong breeze to a storm, the power present in this column of wind substantially increases, as we might expect. If we continue this analysis for a range of wind speeds from 0 to 25 meters per second, a plot of power as a function of wind speed would look something like this. This series of examples is meant to illustrate the significant effect wind speed has on power, given it's a cubic term. You'll note anytime wind speed doubles, this represents an 8-fold increase in power, where 8 is 2 raised to the third. Going back to the initial setup for this problem, you'll note this is data specific to a 1.5 megawatt rated wind turbine, where the nameplate rating of 1.5 megawatts occurs at a specific rated speed, in this case 12 meters per second. As we demonstrated at 12 meters per second, the wind presents an input of roughly 4.8 megawatts. Given the turbine produces 1.5 megawatts of usable electrical power output, given an input of 4.8 megawatts at the rated speed of 12 meters per second, this represents an efficiency of roughly 31%, which might seem unusually low at first inspection, However, realize that there's a hard maximum imposed by physical reality called the Betz limit of roughly 59% that wind turbines cannot overcome, principally because extracting any more than 59% of the available power from a column of air would essentially stop the air from moving through the rotor-swept area as more and more dead air particles pile up behind the turbine. So 31% is actually a pretty respectable efficiency, especially considering wind is free and doesn't pollute the environment if you let some slip through your grasp. The same cannot be said for gas engines, which typically have an efficiency for only 20 to 40%. Not only is gas expensive, the byproducts of combustion take a toll on the environment. Besides the rated speed, other important speeds, specifically the cut-in and cut-out speeds, define the operational range of a wind turbine. For this particular model, we're assuming a cut-in speed of 3.5 meters per second when the turbine is first capable of exporting usable power. Anything below 3.5 milliseconds, it's not worth its time and it just sits there with a dumb look on its face, waiting for something interesting to happen. Assuming a constant 31% efficiency for the range from 3.5 meters per second to 12 meters per second, which is not entirely accurate, but suitable for our purposes, at 3.5 meters per second, the turbine consumes roughly 120.2 kilowatts of incoming wind power and outputs roughly 31% of this, or 37.2 kilowatts of usable electrical power. A graph of power output as wind speed increases from the cut-in speed of 3.5 meters per second to the rated speed of 12 meters per second shows that the usable power output increases substantially given the cubic velocity term up to the rated power of 1.5 megawatts. During this period from the cut-in to the rated speed, the turbine is effectively desperate to grab as much incoming power as it can from the wind and sets the pitch or angle of attack of the blades such that they intercept the maximum amount of incoming power. This being said, there's a practical limit to the capacity and lifespan of the mechanical and electrical components comprising the turbine, and beyond the rated speed, this turbine starts taking active measures to protect itself and ensure its longevity. This manifests itself as the turbine flatlining output at the nameplate rating at speeds above the rated speed and below the cutout speed. For this example, from the rated speed of 12 meters per second to the cutout speed of 25 meters per second, the turbine output remains at 1.5 megawatts despite increases in wind speed and the resulting increase in incoming power. One of the principal means of regulating output is by pitching the blades, such that they progressively shed more and more wind input. Speeds above the cutout speed, the turbine effectively ceases production by aerodynamically braking the rotor with such an extreme pitch blade angle. And if this isn't enough, it can take additional steps to protect itself, such as yawing or turning out of the wind and applying brakes. Beyond the typical survival speed of around 60 meters per second, it's anybody's guess whether a turbine crumples, falls, folds, or just straight up flies away. For this particular example, 77-meter 1.5 megawatt wind turbine, we're presuming an operational range from 3.5 meters per second to 25 meters per second, with a rated speed occurring at 12 meters per second. This is a wind turbine power curve and featured prominently in all the sales and technical documentation for every wind turbine ever sold. Pretty much all wind turbine power curves look like this, so you should probably familiarize yourself to its shape and the reasons it takes this recognizable form. You'll note the characteristic steep ramp up from the cut-in to the knee at the rated speed, and the flat line from the rated to the cutout speed, at which output drops off. From the cut-in to the rated speed, the blades are pitched such that they gather as much wind as possible. From the rated to the cutout speed, the blades are progressively pitched such that they spill more and more wind and output remains at the nameplate value. One particular turbine model might have an earlier or later cut-in or cut-out speed, and the rated speed might be slightly shifted left or right depending upon the design, but most power curves look like this. Case in point, consider a 100-meter diameter, 1.7 megawatt wind turbine with an earlier cut-in speed of 3 meters per second, a rated speed of 10 meters per second, and an earlier cutout speed of 23 meters per second. Compared to the previous 1.5 megawatt example, it seems to favor a low wind region given the leftward shift. Another giveaway is the comparatively larger rotor size. This turbine maximizes surface area to extract as much power as it can from relatively low wind speeds. Consider the power input at the rated condition of 10 meters per second. First, calculate the rotor swept area for the increased 100-meter diameter. Substituting 100 meters into the circular surface area equation yields a rotor swept area of roughly 7,854 meters squared. Extending each blade by 11.5 meters increases the diameter by 23 meters, which almost doubles the rotor swept area of the previous illustrated example. presuming air density remains the same at 1.204 kilograms per meter cubed. Substituting this density, larger surface area, and new rated speed into the power formula yields an input of roughly 4.7 megawatts. You note this significantly larger 100-meter diameter turbine experiences roughly the same input at 10 meters per second, as does the smaller 77-meter diameter turbine at an increased speed of 12 meters per second. Makes sense. The 1.7 megawatt turbine with a larger rotor is designed to take advantage of lower wind conditions. You'll additionally note at this rated speed, this turbine yields 1.7 megawatts of usable power output, given roughly 4.7 megawatts of input. This is an increased efficiency rating of roughly 36%. It's still below the BETS limit, but more efficient than the first example. All right, thus far we've taken a look at how wind speed and area affect input power. Now let's take a look at how various operating conditions can affect the power input to a wind turbine. Consider the 100-meter diameter turbine installed not in some dusty hot cornfield in the Midwest, but rather an offshore wind farm where the marine environment's cold, moist air has a slightly higher density of, let's say, 1.225 kilograms per meter cubed. This might not seem like much of a difference, but consider the effect increased air density has at a wind speed of 10 meters per second. Substituting the given data and the new density into the power formula yields an input of roughly 4.8 megawatts, essentially 100 kilowatts more input simply because colder, moister air is more dense. Not only is the air denser in offshore conditions, higher wind speeds occur more frequently. This is a win-win scenario for offshore wind farms, and one of the reasons offshore wind is receiving so much attention right now. Speaking of density, let's take a quick look at hydro turbines before we close out this lecture. Water is around 1,000 times as dense as air, so hydro turbines needn't be as physically massive as wind turbines. This being said, hydro turbines work slightly different than wind turbines. Yes, there's a flow of matter through them, however they additionally work using a pressure differential from the top of the reservoir to the outlet. One method of determining input power to a hydropower turbine demonstrates in power as density in kilograms per meter cubed times gravitational acceleration in meters per second squared times head, the distance from the top of the reservoir to the outlet in meters, times a flow rate in cubic meters per second. This being said, finding these quantities in usable format is somewhat difficult because most dams in the U.S. were built using U.S. customer units and may necessitate intermediate unit conversions. For example, consider a 52 megawatt rated hydro turbine with a 74-foot differential from the top of the reservoir to the outlet, running at the rated capacity with a flow rate of 12,250 cubic feet per second. Water has a density of 1,000 kilograms per cubic meter. The acceleration of gravity is 9.81 meters per second squared. We need to put head and flow rate in usable units of meters and cubic meters per second. Let's ask the internet. ConvertUnits.com says 74 feet is roughly equivalent to 22.6 meters, and 12,250 cubic feet per second is roughly equivalent to 346.9 cubic meters per second. Substituting these values into the hydropower equation yields an input of roughly 76.9 megawatts. Given this turbine produces 52 megawatts of usable electrical power output when supplied roughly 76.9 megawatts of hydropower input, this represents an efficiency of roughly 71.8%, which is actually pretty poor considering a modern Kaplan turbine can reach an efficiency approaching 90%. This being said, 71.8% efficiency is not bad considering the turbine I modeled this data on was installed in 1937, back when children used to ride donkeys to their jobs in coal mines. As with wind turbines, the input power to a hydropower turbine is dependent upon these input properties. Turbines with more differential between the top of the reservoir and the outlet, i.e. higher head, and those turbines with larger draft tubes can accommodate higher flow rates and thus experience more input power. Now that we've got an understanding of those properties that influence input power to wind and hydro turbines, let's compare and contrast the two. You'll recall wind turbines operate inside a range of wind speeds and directions and need to actively pitch their blades and yaw to follow the wind, which is uncontrolled and uncontrollable. In short, a wind turbine needs to chase the wind like a cat does a laser pointer. Hydropower turbines are different in that rivers aren't known to frequently switch direction, nor does flow rate normally spike up and down. This means hydropower turbines essentially operate by maintaining constant input from an available resource. The management of flow rate is largely performed by opening and closing what are known as wicket gates, using a bull ring and two hydraulic cylinders. As one cylinder extends and the other retracts, they turn the bull ring such that the wicket gates open like Venetian blinds and allow more water in. Conversely, as one cylinder retracts and the other extends, the bull ring rotates in the opposite direction such that the wicket gates close and allow less water in. In addition to modulating the flow rate using the wicket gates, a Kaplan turbine can additionally pitch the blades, as do wind turbines, to capture more or less of the incoming flow. If you think about it, the primary responsibility of a hydropower turbine control system is not to respond to wildly changing input, as would a wind turbine, but rather keep input inside a defined range that maximizes efficiency. The logical extension of this different means of control has some pretty important consequences to the methods one uses to generate power from wind versus the method one uses to generate power from water. Given a hydro turbine has the luxury of maintaining a steady flow of a stockpiled and available renewable resource, most large-scale hydro turbines, not all, are synchronous generators that run at a constant speed. Wind turbines, in contrast, need to respond to often wildly changing wind speeds and directions and are more suited towards variable speed generation schemes like comparatively simple induction generators or slightly more complicated doubly fed induction generators with partial conversion. Viewers will recall we discussed synchronous, induction, and doubly fed induction generation in great detail in the Motors and Generators playlist, available at the Big Bad Tech channel. If you really had to use a wind turbine to generate synchronously, often the only way to do so might be through what's known as full conversion, where the wind turbine runs at whatever speed suitable for the conditions, and the generator outputs wild three-phase AC. That is three-phase AC without regard to voltage magnitude, frequency, phase shift, or phase sequence. And this wild three-phase AC is entirely rectified to DC and then inverted to grid-compliant three-phase AC with a proper magnitude, frequency, sequence, and phase shift suitable for export by a power electronics device known as an inverter. We'll take a look at some of the power electronics devices that make this possible in greater detail in later lectures. All right, before we wrap this lecture up, I need to fulfill the promise I made at the beginning and authoritatively answer two of the three most common questions I'm asked about wind turbines, notably why they so big, why they so tall, and why they painted white. Why they so big? The power formula demonstrates that a larger surface area intercepts more wind. Turbines favoring low wind regions tend to have longer blades, larger diameter rotors. Why they so tall? The wind power input formula demonstrates that at higher wind speeds, yield substantially more input. Horizontal axis wind turbine generators place the rotor on a tower well above the slow-moving air at the surface and immerses it inside a region of unobstructed flow. At the surface, there exists wind shear, which is a change in wind speed and direction over a short distance, and turbulence, which is a chaotic, unstable flow. Getting out of this disturbed region is perhaps the horizontal axis wind turbine generator's single most important advantage over vertical axis wind turbine generators, which place the generator at the base and spin vertically. Although freed from the necessity of yawing to track the wind and climbing during maintenance, vertical axis wind turbine generators simply don't work well because they are constantly beset with poor wind conditions at the surface. As a general rule, an object of height h disturbs a hemispherical region of air 20h in diameter and 2h in height. You'll note this includes a region of 2h in front of the object as air piles up in front of the obstruction and slows down. Given wind speed's substantial contribution to wind power input, it makes sense to maximize this contribution and get out of the disturbed region and into space with maximum wind speed. Before I address the final question, I should note that although wind speed is the single most influential factor in determining instantaneous power output for a turbine, I'll have you know that far more importance needs to be placed on average wind speed rather than some peak wind speed for a particular location. Wind turbines, after all, are in the business of making energy, and energy is power times time. This means a turbine installed in a low wind environment that regularly experiences low wind on a nearly continuous basis. Again, even if it's the low end of the operational range of a particular turbine, it might actually produce more energy than would a single larger, more powerful turbine operated at the rated speed only on occasion. I'm of course referring to capacity factor, which is the percent turbine runs at capacity versus sitting idle waiting for something to happen. For this reason, there's often a lengthy wind speed data collection and analysis period prior to installing a turbine to see if it's worth the expense of doing so. Lastly, why they painted white? I don't know. Maybe there was a sale on white? I suspect this has something to keep visual disturbance to a minimum, and white might blend into the sky better at distance than other colors. Personally, I think it'd be super cool if every turbine was tagged like Patrick Vogel's 2025 animation Wholeturbine, but hey, that's just me. I'll put a link to Patrick's video in the information section below. Check it out because it's pretty cool. All right, that's all I got for you today. In conclusion, this lecture discussed wind and water power and discussed those properties like density, area, speed, head, and flow rate that influence it. Additionally, we examined basic control mechanisms and generation methods used by wind and hydro turbines to manage power output. Remember to review these concepts as often as you need to really drive it home. Imagine how well a lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.